5 to 10 minutes for bathroom, things like that. Just the whole shebang, just in case anybody needs it. Thank you. Yeah, we're good? All right. All right, so you guys know this is Orgo 2, so we're going to get started in a minute here. Just wait for any late people coming in, things like that. We'll leave that up for a second. Okay. All right, we can get started now, guys. So essentially my goal for this is going to be mainly a concept review. I'm just trying to make sure you guys know all your mechs, all your concepts, all your general rules and things like that, so we're all on the same page. And then later tonight there will be Jessica's session, which is going to be more practical, more practice, more suited towards the ACS. So this is more of a background check, make sure you know what's up before you get there. So ideally, if you guys want to take a picture, I'm going to put this up. These are the topics and subjects that are prioritized within the ACS, each on chapters. Let me see if I can get it so you guys can see all of it. Okay. Oh, no, it's all of them. The highlighted ones, because this is the one I used when I took the exam, so the highlighted ones are things that I struggled with, so that I focused on. There's a back, so let me know when you guys are good. All right, and then there's that bottom part if you want to grab it. And the back. Chapter 25 isn't really touched on that much, that's why there's not a lot of notes on it, but it's a good look through just to see, just in case, all right? So let's start from the top. So the first thing you guys worked on, ideally, was resonance, conjugation, doing your 1,2 and 1,4 additions. So let's start with what conjugation is. So conjugation, in theory, is when the p orbitals overlap. And there are 3 or more adjacent atoms. So essentially, the most familiar position that you guys know is the 1,3-diene, which looks like this. And this is the best example of a conjugated system for you, because ideally you have that overlap between these two bonds, and we can draw resonance in a lot of different ways with this section. So especially when we get into Diels-Alder mech, you're going to see it's mainly between dienophiles and dienes like such. So let's just get a few factors out of the way. So as far as when we're talking about the carbo cation stability, you guys remember in Orgo 1 it goes primary, secondary, then tertiary, going off of when we have our carbo cation looking like this. This one is known as primary. Then you have 2 R groups with an H. That's secondary. So when we're talking about our allylic carbocations, the ones created by a resonated diene, it's going to fall in between secondary and tertiary as far as carbocation stability. So this is our allylic, and then you have tertiary. And so we have increasing stability. So those are good for your multiple choice questions, just knowing about stability and things like that. If I ever write off the doc camera, just let me know and I'll move it up, all right? So just real quick, conversing about some of the size, lengths, and things that may come up on the ACS that they like to know, just know when it's conjugated, this actually does affect bond length, where the conjugated parts, like with the double bonds, are usually going to be around 134 picometers, while this will be 148. So the change this causes is usually in this bond, when it's not conjugated, it's going to be at 153. So the pull between the double bonds creates a shorter bond length. It's just something that they like to talk about. All right. So now let's talk about the actual mech associated with this beginning part. Did you guys get all the stuff from the first page? If you guys who just walked in, if you want to take a picture real quick. Okay, you good? All right. So now let's go to the actual mech. So beginning when we start working with these conjugated systems, the first thing you guys learned was about the electrophilic addition, right? And this was between your thermo and your kinetic products, 1, 2, and 1, 4. So ideally, the general mechanism looks something like this, where you have your conjugated system and you add halide with HBr, right? And this would be defined as your slow step. And if we count the carbons, just so for person, so we have this bond breaking, giving the negative of that, and the double bond pulls on the hydrogen. So this leaves us in a situation where we now have a potential for resonance. And this resonance step is what differentiates the 1, 2 to the 1, 4. So ideally, we create this, but we can also draw resonance to create that. And depending on which resonance structure you use, that will go ahead and define whether you have performed a 1, 2 electrophilic addition or a 1, 4. So if we go ahead and add onto the 2 carbon, right, our bromine is going to go ahead, attach. We have now done 1, 2 addition. While if we use this resonance structure, we add onto the 4, we now have 1, 4 addition. So some things you need to know about this. 1, 2 is the kinetic, right? It happens faster, and it happens within low temps. And again, because it happens faster, it's going to be less stable, right? So essentially, while the major product here is going to be the thermo, and it happens slower. And this can happen under the high temps. Okay. So you guys have any questions on electrophilic addition? No? Good?
It's at high temps, wouldn't the kinetic won't be at high temps since at higher temperatures reactions usually go faster?
See, that's the thing. With higher temperatures, you have more surrounding energy within the system to provide for that slower, longer, more stable product. And that's why within higher temperatures, you have the thermodynamic occurring, because you have the energy to spend, right? When you don't have that extra energy, you're just going to go for the fast and easy, right? It's going to create a more shoddy, minor product in this case, because you're not as stable. You don't have as many substitutions, right? Because we're going off of the less substituted there. So that's why. All right. So moving on. So the next thing we do from there is Diels-Alder, right? Or Diels-Alder, or however you like to pronounce it. So we have Diels-Alder reaction. And so it's taking the same principle we've learned from the conjugated system, and it's saying what happens when we react a diene, right, our conjugated diene with something that's a dienophile. So these are important type vocab things to know for the ACS, dienophile. So essentially, if we look at the net product of what this is going to create, we're going to create, at the end, we're going to have a net of 3 pi bonds breaking. Amen. And then pretty much 3 bonds forming, being 2 sigma and 1 pi. So that's some offhand shot. So now let's look at how this actually happens. So, yeah. If we take our diene and we react it with the dienophile, essentially you have this cyclic motion happen where this is going to go ahead there. And that's just going to result in a single ring cyclic structure with 1 pi bond. Now, some conceptual things to know about this. This reaction needs to happen in the cis position, right? Whenever you see your diene's always going to be cis, right? Because this reaction doesn't happen in the trans. But good news for you, you don't really need to worry about it too much. Because when you add heat to any system, which is a byproduct of energy within any reaction, that heat will transfer and convert this structure from trans to cis. So most of the times, it's a non-factor. The only time you need to consider it is when you have it in a cyclic structure. So when our diene is within a cyclic structure, our reaction must undergo a little bit of a different version, right? We kind of have to think about what happens when there's steric hindrance caused by the diene being in a cyclic structure. So again, just sticking with the general, your same general reaction is going to occur, but the actual positioning of what happens is you have to think about this part right here. The actual part that closes the cyclic structure is going to be folded up. Because of the steric hindrance and the repulsion of electrons, we're going to take that flap and we're going to bring it up like a house, right? And so when we draw our structure, that's going to go ahead. We have to notate that difference. And so essentially you're going to have that closed structure, but this flap gets folded up, and that's where you have it. Right? And so it's going to look like something like that. And so this reaction occurs the same way even with substituents on it. So for example, if I add a methyl onto the diene right there and there, you're going to see the methyl conversely added right there and there. While if I add methyls onto the dienophile, you're going to see them go there and there. So it's just playing that matching game. So ideally, I would suggest just doing the general structure and from there adding your substituents, and you're going to see it's going to be a lot easier for you, right?
For the substituents on the dienophile, do you have to worry about like writing an actual formula?
Yeah, we'll get to that in a bit. What's up?
There'd be a double bond, right? Like,
Yeah.
between the bars.
Yeah, between the bars where they bond, usually it's going to be because of this formation here, the double bond's right here. All right, thank you for reminding me about that double bond. All right, so like Matt said, let's talk about the endo and exo products then, because depending on the stereochemistry of the substituents on the dienophile, that's going to determine whether it's endo or exo. So essentially, exo, you can equate that to equatorial. And endo is going to go ahead and be axial. Now the endo product is always preferred. So the endo is going to go ahead and be your major, while this becomes your minor. So how you know how to draw the stereochemistry of your substituents on the the dienophile, would be the question will have to tell you whether you're looking for your major or minor product. So depending if you're looking for the minor, if it's minor, you're going to see these substituents here be an axial, right? While if it's, other way around. If it's exo, it'd be equatorial. And then endo is axial, right? Now, ideally, just one thing to know, right, as far as the Diels-Alders concerned, is just some things they can ask you about it is just know that it is a concerted mechanism, right? So Diels-Alder, it's concerted. Happens all in one step. And it's initiated by heat. Right? Okay. Okay, so next. With the note, with every mechanism I'm going to cover today, just always be sure that you are capable and aware of the retrosynthesis of it. Be able to do it in backwards. So if I give you a product, you should be able to identify the product as what mechanism it is and break it into its base parts. Because the ACS does like to do that. It does like to give you a product and then ask you for reactants. Okay? Okay. So going on to the next thing. So now we have talking about aromaticity. So aromaticity is not too difficult as long as you remember the rules. Okay, so there are 4 rules that must be followed. One is that the structure in question must be cyclic. If it's not cyclic, you already have your answer. It's not going to be aromatic. 2, the structure must be planar, which you're looking at the stereochemistry. Make sure there's no dashes, no wedges, okay? 3, it must be completely conjugated, which is that the double bonds are always only one bond length away from each other. So it's double bond, single bond, double bond, single bond. No matter where you are in the structure, there must be a double bond, one single bond lengths away. If it's not, then you have broken that rule. You're not completely conjugated. You can't be aromatic. Right? 4 is Huckel's rule. Right? And Huckel's rule basically breaks down to 4n plus 2. Now, you can always remember that formula, right? Or you can just remember that it starts at 2 and you just add 4, right? 4, 6, 10, 40, right? You're just adding 4. Or, excuse me, I did that wrong. You're adding 2. So it would be 2, 4. So you just follow the rules. So you count. Yeah, let me just scratch that out. So it would be 2. No, I had it right. It's 4. I can't do simple math, guys. 4, and then from there it's going to be 2 would be 8, then 10. Yeah. 1 is 4. Yeah, it's 6. Yeah, and then 10. Yeah, thank you. I don't know. Simple math. I'm fried today. But yeah. So you can always remember the pattern. Go 2 and then just add 4 from there. Or you can follow the formula, right? So if you memorize the formula, all you have to do is plug in any whole number into n, and that will give you the number of pi electrons that are available within aromatic structures. What's up?
Solve for n, then zero value, it's integer or something, right?
Yeah, so ideally, right, if I give you a structure, for example, I go ahead, just a simple something like that, right? So this is a fully conjugated system. Everything's one bond length away. And then you count pi. So you have 2, 4, 6. So we have 6 pi electrons, right? So now we look at Huckel's rule and we think, is there any number I can plug into n that's a whole number that when I plug it in, it'll give me 6? Well, yeah. If I plug in 1, I get 4 plus 2. That's 6. So that satisfies Huckel's rule. Now, if I only have 4 pi electrons, for example, let's say something like that. So I have 4 pi electrons. There is no whole number that I can plug into n that will give me 4. See, because if I put in 0, I get 2. If I put in 1, I get 6, which means I would need like 0.5. 0.5, 4 times 0.5 equals 2, plus 2 equals 4, which means it breaks Huckel's rule, right? So that's how you use Huckel's rule, right? So the idea here is if the structure breaks 2 or more rules, it's non-aromatic. Uh-huh. If you have the negative and they can be acted towards resonance, then yes. So for example, if you have like a nitrogen protonated by H, its lone electrons would be considered towards resonance, right? Then you can count it. Lone pairs on a carbon, yes, can be counted. But if you just have a nitrogen, then no. And I'll show you an example in a second so you can visualize it, right? So if it breaks 2 or more rules, it's non-aromatic. If it only breaks Rule 4 and satisfies everything else, it's anti-aromatic. And then obviously if it satisfies all 4 rules, then it's aromatic. So, for example, if I give you something like this structure here, right? Like a pyridine like that, would that be aromatic? So 1, we check, is it fully conjugated? So I have 1 bond, 1 single bond, 1 double, 1 single, 1 double, 1 single, 1 double. So yes, it's conjugated. I don't see any dashes or wedges, so it's planar, and it's a complete ring. It's cyclic. So now Huckel's rule, I count my pi electrons, 2, 4, 6. Now I don't count these electrons because they're within the s orbital. They're not in the p. So these don't count towards it. So this would be 6 pi electrons, which, as you know, because of Huckel's rule, 4 pi plus 2, or 4n, satisfies the rule that is aromatic. Now, if I was, let's say this same structure, the pyridine was protonated, now we have this. Well, now these electrons do count towards it, and now we have 8 pi electrons. But we also have multiple problems now, because now we're not conjugated, because we have 2 groups of pi electrons right next to each other, not a bond length away. And so this would be, so that breaks the conjugation rule. And then if we look at 4 pi plus 2, or 4n, if we put in 2, that gives us 8, 10. If we put in 1, that's 6. So it also breaks Huckel's rule. So this structure here would be non-aromatic. And now, but what if we do lone pairs that are just on the carbon? For example, this structure here. Would that be aromatic? So now it's planar, it's cyclic, Is it conjugated? Well, we have 2, 4. These lone pairs can draw resonance, right? We can bring that out, and we can create a conjugated system, right? We can always have it because these are delocalized. Both of these bonds are only one bond away from a pi bond. So it is conjugated, and then we have 2, 4, 6 pi electrons, which is part of aromaticity. It satisfies Huckel's rule. So that is aromatic. Does that answer your question with like the electrons and stuff like that? All right, glad to hear it. Okay.
Is there something for like a positive charge?
Yeah, there is positive charge. Positive charge just opens the door for resonance. So if you have enough electrons and then it looks like it's not conjugated because you have 2 pi bonds next to each other, if there's a positive, you can move that double into the positive and it becomes conjugated. So that's another way they might try to trick you.
What I
But
was thinking is like, oh, if there's 3 bonds and a positive, then it'd still be 6 pi electrons.
exactly.
Count positive.
Yeah. Okay. All right, so now let's go into, after that, we now have our Friedel-Crafts, right? And so these Friedel-Crafts are basically broken down into 5 main mechs. So we have the simplest of them all, which is halogenation, right? Where we use, just going off of the general mech, so if we have a cyclic ring and it's fully conjugated, right? The whole point of these mechanisms here is to activate a conjugated ring, which is usually very stable. Benzene rings are extremely stable. They don't want to react. But sometimes we want to add substituents to them. And so we use one of these 5 mechanisms to activate the ring and then interact and add a substituent. So just a basic thing. So X, in this case, I'm going to say is a halide, right? So you're going to react X2 with FeX2, or any metal that shares a similar charge, right? So any metal with a +2 charge there will work. And you're going to end up with the cyclic benzene ring, conjugated and all, with the X, right? And so these ones, going back, and what we need to take into consideration with this is as we add more and more substituents, we need to be able to tell where on the ring are they going to be added on. And we define that by using directors and activators, or directors that are deactivators, ortho, para, and meta, right? Yeah, so for halogenation, though halides are deactivators, in this case, they're going to act as ortho-para. And just a quick reminder on what ortho, para, and meta are, right? If we have a ring and a substituent is 1 carbon away, 1 length away, that's ortho. If they're 2, that's meta, and then para would be 3 away, right? So when you use halogenation, you're always going to add your substituent ortho-para to whatever's on the ring. Or if it's an empty ring with just the hydrogen in this general mech case, we can just add it, right? And so how these mechanisms work is that step 1 will be creating an electrophile. These electrophiles is what activates the ring and allows for the substituent to add on, right? And so in halogenation, your electrophile will either be Cl plus or bromine plus or ... or whatever halide you decide to use in the case of X, right? So the next one will be nitration, which, like the name implies, we're going to be adding NO2 onto our closed ring. And in this case, we use HNO3, SO4, to go ahead and create, where in this case our electrophile is NO2, and this one is a meta director. And meta, in this case, are things that are deactivators. So this is a activator. Right? We good there? Usually they like to ask retro on this one. They'll give you a product, right? They'll give you a ring with 3 substituents onto it, like NO2, Cl, or SO2, right? Or SO4, right? And based off of whether they're orthopara or if they're an activator or a deactivator, you need to be able to determine the order in which you added on those reagents. And we're going to do an example problem once I get through all of those. Okay? The electrophile for step 1, creating the electrophile, and then 2 is adding electrophile through nuke attack, right? Each NO2 plus is what the electrophile is in this case. So you take HNO3 and you turn it into NO2, and then the double bond on the right here is what does a nuke attack to add the substituent on. So that's kind of it's good to know these mechs in forms of what is my electrophile, and because if you know what the electrophile is, you know what's being added on. Okay, the next one, right, is going to go ahead and be sulphonation. And all of these are 5 different mechs that have different names, but they all undergo the same reaction, which I'm going to go into a little more detail when I cover all of them, right? So sulphonation is going to go ahead and take our ring, and this time we're adding SO3 and H2SO4, right? And our electrophile in this case is going to be SO3H, right? And so, and this is a meta director. All right. Then we have Friedel-Crafts Alkylation, which is a little specific, right? Because Friedel-Crafts doesn't just add any like SO3 group or a halide. It lets you add on any R group that you really can imagine. You just attach a chlorine onto it, slice the chlorine, create that R group as an electrophile, and attach it. So usually when you have your carbon chains, right, if it's a linear carbon chain, you know you're going to use alkylation. If it's a carbonyl derivative, then you're going to use acetylation. So essentially, we're going to go ahead and add RCl, R group being your carbon chain, and you're going to react it with AlCl3. And that's going to go ahead and add on our R group. And alkylation is ortho-para director, and where our electrophile is just the R group. And so Friedel-Crafts acetylation. Yeah. Ortho-para is always an activator, and the only exception is halides. Halides are the only ortho-para directors that are deactivators. Okay?
Can they only go on to if it's an activated ring?
Yeah. Yeah. More details. Okay. So acetylation, okay, is going to go ahead and be our conjugate benzene ring, the hydrogen, and this time we're going RCOCl, right, which is just a carbonyl derivative, and that will give us the carbonyl derivative with the R group attached. And this one will be a meta-director. And likewise, like all of the other, the electrophile in this case is going to be our R double bond O. That's an O if you can't really read it. Our carbon has the positive charge. Okay. So let's take the mech into a little more detail now. All right. So going into a little bit more detail, when we draw our mech, the general reaction is going to look like this, where we have, right? So the first step is essentially we're going to put the ring and we're going to keep it to the side. We're going to deal with our reagents first. So in this case, let's do halogenation because it's the most broad. So if we have Br attached to Br, right? Essentially what's going to go ahead and happen is it's going to go ahead, FeBr3, we're going to go ahead and attach these two. And so that's going to give us Br, Br, Fe, Br3, right? And so we can create an electrophile by going ahead and cleaving this bond and giving the electrons to FeBr3. And now our reagent is going to be the electrophile. Oh, that double bond was really far. My bad. Oop. Sorry. Is going to go ahead and be the Br, right? Br positive. And then we have the FeBr3 with that negative charge. So essentially from here, that's going to go ahead and attack that. This cleaves that. And so we have, right? And now we're going to go ahead, and this negative from the iron is going to go ahead and take that hydrogen, cleaving the bond and bringing the electrons back down. And that's how we end up with the ring fully conjugated once again. And bromine is now attached. Now, the first step where we create the electrophile, step 1, where we interact with dibromine and FeBr3, that's going to act as our rate determining step. Okay. So the same thing happens with halogenation, sulfonation, nitration. Honestly, all of them undergo this same reaction where we have our two reagents react with each other. They cleave, creating a negative and a positive. That positive electrophile acts as our Lewis acid. From there, the diene on the conjugated benzene ring acts as our nucleophile to do a nuke attack. That attaches it. Our remaining base from the negative charge created from our iron is going to attract the hydrogen, cleaves those bonds, those electrons go back in and create the double bond. And we're right back where we started. Any questions on that? Yeah, we're good? All right, so does anybody want me to go through any one of the 5 mechs in specific and show you how it works with that mech? Or should I just move on and you get the general gist and you can apply it to the other 4? Huh? Yeah, move on? Gotcha. All right. So now, before we go on and go too crazy, we need to identify the retrosynth and just identify how does this affect. So for example, if we have a benzene ring, right? With, for example, I'm just trying to find a good example real quick. So if I have a ring, like you are given right? NO2. So this is your final product, right? So we need to know which order does this happen in. And this is where the orthopara and meta-directors come and where activators and deactivators go. So just off of the bat, once you get used to it, you already know that off of these substituents that are attached, you already know that acetylation has occurred. Yeah, and nitration. So the question is, what order do they happen in? So acetylation is going to be a meta-director, and so does nitration. So that means that there's one more step because they're in para. Because they're in para, we know that these two steps can't be the only thing happening because otherwise they would only be 2 bonds away from each other. So that means we're adding something else in first. And so in that case, we're going to go ahead and say we're going to add, in this case,
Add nitration and then make it NH2.
yeah, that's what I was going to do. Yeah. So we can play around. And so there's a way to convert back and forth between NH2 and NO2. Does anybody know what the key reagent is for that, shifting back between NO2 and NH2? Huh? H2SO4 is how you add it on.
Something with PDC, right?
Yeah, PDC works as well. Honestly, even going back as far as,
HCl and then AlCl3.
yeah, that adds it on. Yeah, you can do either way. Really, it just depends. You'll be given like multiple choices. Usually PDC is like the go-to method here. And then from there, it's simple because once you can add on this NH2 group, so our first step would be adding on NH2, right? So first we start with our ring. We're going to go ahead and add the NH2. That would create, right? Then you're not going to convert it just yet because NH2 is orthopara. From there, you can go ahead and add the acetylation, the acylation, right, using the Friedel-Crafts. That will go ahead and add this on. And then from there, you can go ahead, well, I should have drew it separate. There, you can go ahead and use PDC to convert back into NO2. Right? Another method you could have used, I think Daniel mentioned it, is you could have used alkylation with the R group Cl, which is an orthopara director, and then used KMNO4 to reduce the R group into a carbonyl derivative. That's another way you could have gone. Usually, I think on your ACS, you probably would have seen the KMNO4 used because that roots back to Orgo 1, right? And they love to pull in Orgo 1 whenever they can. So for those of you guys who want to see that, essentially, all we do is we take our ring. Yeah, PDC. But so yeah. And then we go ahead and we can go add CH3Cl with AlCl3, which is just the alkylation, which we'll go ahead and just add our methyl here, our CH3. And then from there, we can go ahead and add the nitration, which is HNO3, H2SO4, and then we can change that with KMNO4, and that will create our final product. Yeah. And that's how you get it. So always check, make sure you can identify based off of which substituents you have, what mix you're using. Then always check whether they're in the proper ortho-para position, and that should give away if there's a third hidden step. And from there you can go on. Yeah, nitration is meta, right? But because we added, think about it like traffic, right? So we've added the R group first through acetylation, right? We've added, or alkylation, my bad. We've added alkylation, so we have our R group. So now that we're adding the meta group, because the R group is already on, it's directing ortho-para. It's there first to direct. So you always go based off the substituent that's already on. It's once they're already attached, that's when you would go ahead and direct that one. Does that make sense? So it's not what you're at, it doesn't direct itself, it directs other substituents that are coming on after it. All right. Okay. So I'm just going to cover this real quick because I don't think this should be a huge focus on your ACS, but it's still good to know. Just going back, they like to root. Just know that as far as ionization, when you have your R groups, so if pH is lower than pKa, you're going to protonate. So a good way of remembering that is low pro, right? pH is lower than pKa, protonate. If it's the other way, pH is greater than pKa, you're going to go ahead and deprotonate. And so cases like that, you'll be given a structure. For example, and each substituent here is going to have a pKa, right? pKa is going to be and then I'll tell you in solution the pH is equal to something. In this case, I'm going to say pH is at 1.0. So then you look. So here, for this substituent, pKa is 2, pH is 1, so pH is lower than pKa, so it protonates, so that hydrogen belongs there. Good. Here, pKa is 9, protonates again, H3 with a positive, good, NH3 positive, and they're all above, right? But if I had, let's say, a pH of, for example, let's say 3. Well, in this case, this one that has a pKa of 2 is going to lose its hydrogen and it's going to become a negative. This one is still 9, so that stays the same, and NH12 stays the same. Then you count the charges, so we have a negative, a positive. Positive, our overall charge is +1, and usually they like to ask you about the net charge after ionization has occurred. So that's how you do that. It's straightforward as long as you remember low pro. Right? Yeah, they'll give you the pKa's and they'll give you pH. You don't have to memorize that. Okay?
So when we turn the pH to 3, that OH became negative?
Yeah, because it has a pK of 2. which means when pH is above pKa, it deprotonates, so it loses its hydrogen. When it loses its hydrogen, that oxygen has 7 compared to its valence of 6, so you get negative. Okay. Okay, so let's get through one more chapter before we get on break, because then that's the halfway point. All right, so the next thing we learned about was carbonyl groups and their derivatives. So just so you guys, we're all on the same page, a carbonyl group is anything with double bond O to the C, and this can be anything from aldehydes, ketones, amides, going double bond O, R, and again, esters. It's important that you guys remember these functional groups from Orgo 1. And acid chlorides. So we're all on the same page, right? So from here on out, all we're going to be doing is playing with carbonyls and seeing how they differently react. So ideally, we have our nucleophilic addition, which just simply takes our carbonyl derivative, right? In this case, we use a ketone, right? And we're going to apply a nuke attack in the presence of water. This will all, essentially, you're going to move up the bond, create a carbocation. That nucleophile will attack, right? That's going to create this off shift on our ketone. Right? Then we want to shift it back down. But in the presence of water, just remember, if water is available to protonate, we can go ahead and do that. And so that goes ahead and creates OH. Say that again? Yeah, so essentially if you have water in presence to protonate, then it doesn't kick off. But if water is not in presence, I'm going to show you, that's when we have to compare our leaving group to the nucleophile to see which one gets kicked off when the electrons from oxygen come back down into the double.
So we're going back to where OH is good,
Yeah, so essentially, so this is if water is present. If water isn't present, we have the same reaction, right? Undergo, where we go ahead, create that. Then when this comes back down, one of these R groups, if one of the R groups is a better leaving group than the nucleophile, it will be booted off and we're left with that. Right? So it's good to keep in comparison like the strengths of leaving groups. What's up?
Like how do you determine if, say, R groups is better or worse leaving group?
From there, there's a lot of methods. It's essentially just, there's a way of memorizing it. Like, so it's kind of, depending on which chapter you're using, you're going to use different methods. So when you're talking about more acid bases, you're looking at the acidity of something and whether it creates a stable conjugate base or not. Yeah, like for example, like chlorine, extremely good leaving group. You don't usually want to use it as the nucleophile because it tends to leave and it's unreactive. Because not many things are better leaving groups than chlorine. So you add the chlorine and then the chlorine comes right back off. It doesn't react. It doesn't do anything. So usually hydroxides, things like that, tend to be very good to attach. Yeah, I do. I'm going to do that in just a second. So let me see. Where is it relevant? I know I have it here. Because I have that chart in the chapter that's related to all the stuff. Okay, so I'm going to go ahead and finish this. I'll find it over break, and then I'll start once we get back from the break with that, all right? Okay. So now going off of that. Yeah. So yeah, I can finish this. So let's just talk about the reducing agents of carbonyl groups. So essentially, we have two main reducing groups for these carbonyls, and this is going to be LAH and NABH4, right? So essentially, LAH is your universal reducing agent, excuse me. It's very reactive. It's going to reduce everything. If there's something to be reduced, any double bonds, any H's, anything that can be reduced, it's going to reduce it, right? Well, you have NABH4, right? Which is, again, not as reactive, and it's because it's only reactive towards ketones and aldehydes, right? So example, if we have our ketone here, and we react it with LAH, this is simply just going to go ahead and reduce to that, and NABH4 will do the same exact thing. So these things are pretty synonymous in function and purpose. The only difference is NABH4 is going to be selective towards ketones and aldehydes. And then again, if we look at our aldehyde, and we do LAH and NABH4. And just a side note, LAH is usually paired with water, while NABH4 is usually paired with methyl hydroxide. And you're going to get the same thing of that. Yeah, NABH4 is paired with MEOH, methyl hydroxide. Okay. So just a quick review from Orgo 1, just talking about different selectivities of reducing agents when you have your carbonyl groups. For example, let's give us a cyclic carbonyl group, right? So now we have two different things. We have the carbonyl and we have an alkene. So if we want to be specific towards things, right, if we use one equatorial of H2PDC, right? Yeah. Right? That goes ahead, that H2PDC in one equivalent will prioritize reducing alkenes. So you're going to focus on this one, so you get that. In excess, so H2PDC in excess, right? Whoopsie daisy, excess reduces everything. Okay. While NABH4, if you remember, it's only going to go after the carbonyl group. So when we use NABH4 in this situation, it's just going to simplify the carbonyl and leaves, oh my goodness. Yeah, that double bond is a single bond, my bad guys. And it just leaves the alkene alone. Good? Yeah. H2PDC. It's PD-C. I just kind of ran out of space there. Okay. Yeah. Okay. We're good here? All right, we're almost done with this. All right. So next, the next set of reducing agents are going to go ahead and be Diels H. And this one's reactive mainly only towards esters, but there's a little caveat with that. Esters. Yeah, that's the caveat. And it's milder reducing agent, right? This one's most proficient in low temperatures, right? And so it's reducing only towards esters, but there's a little caveat being that it can work with acid chlorides too. So when you think about it, Diels H and the next one, Diels-Alder 3, are kind of paired because they can kind of mix, where they have a specific purpose, which is mainly for Diels is ester. Diels-Alder 3 is going to be mainly acid chlorides, but they can be intermixed and you can switch their function. I believe that's a little side note made in your textbook, and if you're in Fraser's class, he expands on that quite a bit. Makes me look like an idiot. That was so funny. All right. So the next one would be Diels, or that's not a B. I don't know what I'm doing here, guys. Or 3H, right? And this one is reactive only towards acid chlorides. Yeah, that's OR. And these can intermix. So Diels H technically can react with acid chlorides, and Diels-Alder 3 can technically react with esters. All right. So you don't really need to know the main reaction of all the reducing agents, but you do need to be aware of how does LAH do its job, because they all follow the same similar mechanism, but LAH is what is going to be mainly being used. So when we reduce with LAH and water, essentially we're going to go ahead and get that. And so keep in mind, we're going to react with two equivalents of LAH. So let's see how that actually works. So when we have this, this is going to go ahead and react with the LaH3, which just stands for aluminum hydride, right? It would usually, but here when we do two equivalents, they're going to create like this kind of cycle. You're going to see it in the mech, and that's why I'm bringing it up. It's a little bit of a extra. One equivalent all the way, but here you're going to see the reaction. And even this, we can keep it going until we get to the primary alcohol, right? I'm just showing you the reaction that you actually need to know for the ACS, because from there it's just proton shift, finish off, done, and you have your primary alcohol, excuse me. Okay. Not necessarily. Okay, so how do I put this? You need to know the important part of the reagent and the reaction is how you get to the point where you have the aldehyde, and then simplifying the OH, I'll show you on the side, but it's not as important because it's a mech you've already done. Does that make sense? Like the simplifying of aldehyde to a primary alcohol is something you covered in Orgo 1, but this is, I'm showing you what's actually new. I'll notate it in the notes when you see, right? So again, we're going to go ahead and follow that. So this just goes up. So we're going to be O negative. Just notate that H. Cl. Gonna go ahead and react with, and when we react with the second step is when we're gonna go ahead and react with the aldehyde, which is gonna act as. So that goes that, this cuts like so, and so when this comes back down. And then we react it again with HAlH3, and so that's the intermediate step. So this is the new part going off of the reaction I showed you with the carbonyls. You remember the general mech where it was double bond O to the ester, and then you attack with the nucleophile, then the R group gets kicked off when you bring the double bond back down. That's what is new, and that's what I was showing you. So now is the part you already know where we reduce and we go ahead and bring it to a primary alcohol, right? Right? And so from there, when you go ahead, you react, do that, it's going to be the same steps again, except this time we now have O negative with the H, and with water, we can go ahead and protonate that, and that will give us the primary alcohol. So intermediate. Do you see what I'm saying there? Yeah. I'm sorry, I worded that a confusing way. If it's Diels, yeah, no, because Diels still, it is a milder reducing agent, but can it? I think it stops at the aldehyde, yeah. Yeah, it's milder, it's going to stop at the aldehyde when you use Diels. Okay, so from here, I'm going to give you guys like a 5-minute break. If you need to use the restroom, get anything, we'll come back and collect at 6:11, and we'll finish up. Yeah, for sure.
I got the ACS.
Yeah.
Like little packet thing.
Yeah.
What would you say would be like the best way?
In my experience, and everybody that I've talked to and everything, the best way is just to sit down and grind through that booklet, like the ACS booklet. Just get from cover to cover, do all the practice questions, do everything, because it's good, like, yeah, it's really just the way they're worded, because if you can understand, like, the mechs and things like this, you'll be fine. It's just putting that into practice using ACS method. You're going to find that working through the ACS booklet will be the most beneficial thing to you, right? That's what I recommend. Yeah, just sit up and grind. Just get through it. Get through the booklet and make sure that you're familiar with most questions.
I think I'm like half, like a little less than halfway through it right now.
Yeah.
But I feel like the most thing that I was having trouble with
Yeah.
was just kind of like the acid and basis stuff.
Yeah, that's all Orgo 1. If anything, I would actually suggest maybe sitting in on one of the Orgo 1 sessions too, because they can help you a lot with that, just re-jogging your memory.
I feel like Orgo 2 I kind of...
Yeah, Orgo 2 in my opinion is not too bad.
It's easier than Orgo 1.
Yeah, it's a lot of the same exact stuff over and over. You're going to see like the second half of the session is going to feel like we're doing the same thing over and over as we just keep doing carbonyl nucleophilic attacks and things like that. All right. All right. Also, if you guys could maybe take this time, in front of you guys there are like these little review things. If you could like fill it out for me, I would appreciate that very much. Yeah, thank you. What's up?
Which one would you recommend for Orgo 1 looks better? Neil or Camilla, or if you know them?
I know Emil. He's a pretty cool dude. I would go with that. Plus, it's earlier.
Yeah, yeah.
Yeah, I don't know Camilla, so I can't really talk about her.
All right.
Yeah, no problem. Oh, you're just grabbing the first page? Yeah, I feel you. So how are you guys feeling about this final coming up?
Been doing studying, you know, I figure
Yeah.
I'll just getting into
Yeah, if you guys can, man, there's nothing I recommend more than just going through that ACS booklet because it's just so different. Like, I don't care how well you've been doing on Fraser's or Dowdy's exams, you haven't taken this. Like, do you guys have to take ACS for Orgo 1? Because I think,
went to different schools, so
yeah, so,
It's the same way they do it for Gen Chems because the Gen Chem one is like the accumulation of Gen Chem
yeah.
1 and 2.
Mm-hmm. Yeah, so this ACS is both Orgo 1 and Orgo 2. Yeah.
It's like 60-40.
Yeah, so it's really, but it's standardized. Like, that's what gets most students. The fact that it's standardized, so the language is written in such a way that
it's weird. It's lawyer talk.
just understanding the question is a question in itself.
It's lawyer talk.
Yeah, kind of. Like, they just have a weird way of asking questions. Like, instead of asking you, oh, which one's more stable, they'll go about it in such a roundabout way that it makes things difficult. And for that reason, I would really highly recommend maybe jumping into an Orgo 1 session that we're offering as well, just to jog your memory, because, again, a lot of Orgo 1 topics will be on the exam as well. And sadly, I cannot put the time to do Orgo 1 as well in here. I just got to burn through Orgo 2. Okay. Uh-oh. What quarter is it? Third?
Have a football game going on?
Yeah.
Yeah, no, I'm gonna park in garage H, and then I was like, wait, it's pay.
Yeah, we're losing right now.
What? Did something happen to the quarterback guy?
Yikes. Feels bad, man. Feels bad. I'm not even a football. Yeah. All right, guys. We can get started again now. Sadly, I wish I could give you guys a little more of a mental break, but as it is, we're going to be rushing. We still got 21, 22, 23, and 24 to go over. We've done 16 through 20, pretty much. Yeah. But good news is it doesn't get too bad. Okay, so, yeah, this stuff should be more fresh. So we're going to finish up 20. So now all we got left of 20 is organometallic reagents, right? So out of our organometallic, we got pretty much, you know, the simple ones. We got R groups attached with lithium, which again is intuitively organolithium. You have RMGX, which is organomagnesium. And then you have organocopper. Just two groups. Where organocopper is the least, yeah, it's the least reactive out of the three, and it's the most selective. And pretty much that's just, if they ask you why that is, it's just the carbon to the metal bond, right? The more polar that bond is, the more reactive it is. Because essentially that's what drives your reaction, the charge differential between the carbon and the metal it's attached to.
So it's because that carbon to metal bond is more polar than the rest?
Yeah, or it's less polar. On organocopper, if you're asking why it's least selective, is because look at it. Copper has a charge of +1, right? And so you can fit on 2 R groups onto that copper, where the rest of them you can only fit on 1. And this is supposed to be G. Magnesium and both, lithium and magnesium both have a +2, so you're going to result in a more polar bond. And that's why it's more reactive on organomagnesium versus organocopper. And this is the Grignard, if you remember, and then that's Gilman's. Right. So essentially, let's get into the reactions that you're going to see with this. I can fit some more on there. So the reactions you're going to see at this is these organometallics can act as both a base and a nucleophile. So usually when they act as a base, they're already going to be attached onto the main product, and then they get removed and substituted with another factor, right? So in this case, so if we have conjugated ring, and then we have magnesium bromide attached onto this, here we're going to react as a base, right? And we can react this with, let's say, HOCH3, right? Or we're going to break this bond here. Then this bond is going to go ahead and grab the hydrogen. And so that's going to go ahead and give us just a normal ring with the hydrogen plus CHO negative bonded to the magnesium bromide. Well, not bonded, they're in ions. There we go. Right? So as a base, it's very simple. It's just going to be wherever the H to the electronegative atom, cleave that bond goes to the electronegative atom, and then you swap out the Grignard reagent with the proton. Sadly, as easy as that one is, it's rarely ever going to be the main focus. Usually you're going to see these organometallics acting as a nucleophile. But the reaction as a nucleophile isn't too much different, right? All we're doing is we're switching places. Where we have our original product, we have the organometallic, and we're going to have a R group or a carbon chain attached to it. And our organometallic is going to function in a very similar way as we function in alkylation, where we cleave the bond and then we attach. So you're going to see that as, for example, if we have our carbonyl again, and we react that with ethyl magnesium bromide, we're just going to follow the same line where we go ahead and we go ahead and take that, and so and then we protonate with water. Right? Oh, whoopsie daisy, forgot the H. There we go. Yeah. Usually it's going to be coupled with mag. And if it's not, then all you're going to do is you're going to boot off the leaving group like you do with these reagents. So again, just kind of how we did with the alkylation, we're just cleaving the bond between the organometallic and the R group, and the R group is being attached on. Okay. Last thing to cover about this stuff is going to go ahead and be our protecting groups. What about organolithium? Yeah, well, organolithium has the potential to add both of its R groups on. Usually it's going to add one, but if you have it in excess, you can keep reacting and add both R groups if that's what you're asking.
I'm asking, like, if you have like a ring, right? Would it be like organolithium is going to add to that carbonyl, and then organocuprate would add to that?
Oh, yeah, yeah. You're talking about the selectivity. Yeah, that would be correct. Yeah, okay. So essentially the protection groups, you use them when you want to protect a certain substituent. So it kind of forces your organometallic to react with the opposite end. And that's just to keep substituents or tails protected. So usually the common OH protection groups are would be O bonded to silicone or TBDMS. Right? And when you add your common protection group, once you finish with your reagent, you add a deprotecting group to remove the protection group and finish your reaction. And in this case, Bu for N pleasant is a good one as well. So if we're going to show a reaction with that, for example, if I have right, I'm going to go ahead and add on my protection group. You may see it as PG. PG also stands for protection group, or you may be given the specific one, such as TBDMS. So these, I'm going to write both. They're not two separate reagents, just so you can be exposed to both. So I'm going to notate PG with a little quotation mark. So it's only one reagent here. So essentially, that's just going to attach on to your OH and protect it. So it's going to cleave the bond between the hydrogen and the oxygen, and we're going to have OPG. From here, we can react with our MgCl. I'll do methyl magnesium chloride. And then we'll also react with water. And so that will go ahead and give us this. So instead of the organomagnesium reacting with this hydroxide, we've protected it, and so it chooses the carbonyl instead, right? And so from there, we can just go ahead and deprotect using Bu and Bu4NF. And that will get us back to our original state with the hydroxide. An O on the OH, where? Yeah. Oops. That? This O? Wait. Yeah, that's exactly what I was trying to do. I don't know why I drew the O here. Hold up. So essentially we add it. Yeah. This goes here because what happens is we do the shift up. The methyl adds from the magnesium chlorine. Then we protonate with water, giving us hydroxide. So yeah, I don't know why I put that O there. That is my bad, guys. But yeah, it's like that. All right. Oops, sorry. Okay. So let's move on to the next one. Okay. You guys good with that? Move on? Again, if you guys need to see any of the notes after we're done, they're all in a stack here. Also, you can see my original notes. I'll let you guys take pictures of these two if you guys want. This is just more so you can see them in action. Okay. So next thing we got is essentially Witting reagent, right? So the Witting reagent, is not bad at all. Okay, so essentially the Whitting reagent is an yield A made up of pH3, P, and then we bond that. Oopsie daisy. There we go. Right? It's triphenylphosphine oxide. And so just a quick reminder on what a yield A is, or yield A, or however you may pronounce it, is when you have two opposing charged atoms bonded to each other. So you have this negative carbon bonded to this positive phosphorus, right? I yield it, and that's when two opposing charged atoms are bonded to each other, right? And so when we react to them, right, usually we can react the yield A, or the Whitting's reagent, with a carbonyl group, right? pH3P CH2, right? For example. And so when we do this, we can form alkenes. So that will form something like that. So essentially all we do is we're going to take whatever's on the right side of our Whitting reagent, swap it out with the O and attach it, and then the O is going to attach itself to what's left of the Whitting reagent. This is how it pretty much breaks down. And so we're converting a C double O bond to carbonyl to a C double bond to C, which creates two new carbon-carbon bonds, one new sigma and one new pi, right? And so if we actually look at how that mechanism proceeds, we look at it. I'm going to write it a little differently so you can see what's happening a bit better. All right, so this bond is actually here, but essentially this is the positive, that's the negative. So the lone pairs on the oxygen are going to go ahead and be attracted here, while this attracts to that. So that's essentially what happens. And when you have this reagent happening like this, because of the yield A formation, where you have these two opposing charges, just like we had with the dienophile and the diene, we're going to create this circular exchange where we have the R groups here, O, H3, bond, yeah, like so, where this bond goes here, and that bond goes there. And that will result in our final product of the R group, CH2. Yeah, these should be H's. I don't know why I wrote R. Just quick correction. Bless both of you. Yeah. Right? Any questions on Whitting reagent?
When you're drawing that square shape,
Yeah.
why is there a reason those lines are disconnected? That carbon to the P?
Where? Here?
Yeah.
Oh, that was just poor drawing. Yeah. When you're trying to write fast, things happen. All right. Okay. So now from there we go into Gem-Diol Formation, right? Which is when you treat water it's pretty much carbonyls treating it with water in the presence of a base or in the presence of an acid. And so Gem-Diols are essentially a structure with two hydroxides attached to it. So in this case, we could say it could be OH, OH, R. That's a Gem-Diol. So how can we form these? Again, there's two main ways. We have base catalyzed, where we take a carbonyl group and we treat it with hydroxide. Again, these are water treatment mechanisms where we're treating something with water with the presence of a base or an acid. So we're going to take this hydroxide. We're going to go ahead. This is negative, so we're going to move that up. Go ahead, attach that, just like we have for the 30th time today. Right? And we're going to go ahead and treat that with water. And so in this case, you have the Gem-Diol, OH, OH. Simple. Base catalyzed tends to be a lot straightforward because when you have carbonyl formations and we're doing a nucleophilic attack, we don't have to protonate, we don't have to do any proton transfer. It's just straight and to the point. Right? So now we have the other way, which is going to be ahead and go acid-catalyzed. Promise, follow along, it's not too bad. So we're going to have our carbonyl, but now we don't have the straight up nucleophile we had before. We can't just attach it on as we did before. So instead of doing resonance and going through that way, we're going to have to go ahead and straight protonate. And so when we do this, this creates OH positive here. And we can draw a resonance structure, which is more figurative to our situation, where we shift the positive to a carbocation. From here, we treat it again with water. And so the oxygen is going to go ahead and go there. And so that will give us right? So now we've attached water on, so we have water attached. And so what we can do here is once we have the water attached, we treat it again with water. And that transfers here, and this O transfers here, and we result with hydroxide or Gem-Diol. And remember, for base catalyzed, when you do this, you're going to always end up with your Gem-Diol plus hydroxide. And if you know, once we steal the H and deprotonate with water, we're going to end with H3O. So you know, just pro tip, if you're doing Gem-Diol formation and asks you, is this base catalyzed or acid catalyzed, and they don't give you the actual process of what happens, you need to see what is paired with a Gem-Diol. If hydronium is paired with a Gem-Diol, you know it's acid catalyzed. If hydroxide is paired, it's base catalyzed.
So do you always start with ketones to make a Gem-Diol?
It doesn't have to be ketones. It can be any carbonyl group, as long as you have that double bond O. It can be an ester, it can be an acid chloride. It really can be anything. Okay. Okay, now let's go to Hemiacetal Formation. Okay. So essentially, Hemiacetal Formation is just the internal form using acids, or it can even happen intramolecularly to close a ring. So for example, so I'm going to do acid-catalyzed because it tends to be prioritized. Hemiacetal Formation. So for example, usually this happens only with 5 to 6 membered rings. and it's going to go ahead and close off the rings. Intramolecular can also happen if you have an aldehyde, but let me show you the acid catalyzed. So example, so if we have hydroxide, essentially what we're going to do is we're going to go ahead and react that with an acid. And so this O is going to go ahead, attach that. And so we're going to have go ahead. And so, again, whenever we have the positive hydroxide, we can use resonance to shift that positive down to the carbocation. And so that's going to have the hydroxide attack, right? That. And so now we will have and remember, after we use that acid, we still have its conjugate base in solution. At the top, yeah, that's general notation for acid. Just a proton to a conjugate base, that's acid. And so we still that. So that can be an H3O or whatever acid, really. And so we have its conjugate base left in solution. It's going to deprotonate the hydroxide, and that's going to go ahead and leave us with plus HA. Okay. Okay. Okay, so now let's talk about just nucleophilic acyl substitution, which is pretty much, again, just what you guys have been doing for the last like 2 chapters here now at this point. Orgo 2 tends to be rather repetitive. Right? And this is, again, just defining what we've been doing this entire time, where we have an R group, a Z group, and we're trying to attach a nucleophile. So again, that just goes up, the nucleophile attacks. But now we're going to actually have some rules to it. The Z group, please. And we now have nucleophile, right? So before, when we first introduced this, we were talking about as long as Z, which is acting as our leaving group, is a stronger leaving group than the nucleophile, this reaction will undergo way. And so the more reactive the leaving group is, the better, because let's, for example, if our nucleophile is chlorine, while our Z group is, I don't know, hydroxide at that point, chlorine's just going to leave again, and we're just going to be left with the carboxylic acid again, which means nothing really happened. So ideally, you want to follow this general trend. So here's the list, how it goes. It's NH2, hydroxide, O to an R group, sulfur to an R group, PO4, and then your halides, right? And this is an increasing, so increasing reactivity and increasing leaving group ability.
What is the second last one, the P something?
Oh, PO4. Right? So ideally, you want Yeah. Ideally for this, what you want is you want your nucleophile that's actually attacking to be on this end and your Z group to be on this end. So you want your Z group to always be further right on this list than your nucleophile, because if it isn't, no reaction happens. For example, if my nucleophile is chlorine and my Z group is hydroxide, like we said, you stick with the carboxylic acid. The chlorine is just going to leave right back when you bring the electrons down. So let's look at some general products from here. So just an overall review of what's essentially you need to know based off of nucleophilic acyl substitution is that if you react this with that, you're always going to result in an anhydride. And it follows the same exact mech that I showed in the general. If we react this with hydroxide, you're going to result in a carboxylic acid. Given that your leaving group, your Z group, is weaker than hydroxide. Then if we go HOR, again, you're going to result in an ester. And lastly, but not least, if we do amides, depending on the degree of the group, so if I have H and RH or H and R2, we'll reduce our, I don't know the word I was saying, brain fart. Produce is what I meant to say. There we go. Ha, got it. NH2, R group, and NHR, or double bond, and R, and R. Yeah. So primary amide, secondary amide, or tertiary amide. Okay. All right. So going into specifics, the two mechs that you really need to make sure you know from this one are Fischer Esterification and then Ester Hydrolysis, which are the same mech, just going backwards and forwards. And side note, when we get to Fischer Hydrolysis, if you remember, Fischer Hydrolysis is the main producing key of saponification, soap, right? This should be sounding really familiar because we're actually getting really close to where you guys just were, right? So Fischer Esterification is taking a carboxylic acid and turning it into an ester. So an acid to an ester. And it happens under acidic conditions. So if you're reacting with base, it will not happen. So if they ever give you a carboxylic acid and show the product as a ester, you know an acid must have been used. Okay? If it's a base, then that product will not, that reaction will not run. So starting with our carboxylic acid, when we add acid, it's going to go ahead and react in the general way it has been reacting all throughout this session. Right? That's going to come up, create a carbocation here, which then can be filled in by ROH. And now we're going to have OH. We can react that again with more acid at that point. create water. That's going to go there. Water is going to be a leaving group. And then we can go ahead, use water. Oh, not water, excuse me, I'm a step early. The conjugate base to deprotonate. And then that can also go down. And then we have our ester. What's up, Matt? Because acid is in solution, so essentially you have as much acid as you want to react. Yeah. Ideally, you're going to prefer to use hydronium, though. Okay. Now let's do it backwards. I'm going to change pages because now ester hydrolysis, on the other hand, which is the backwards mechanism, can happen through both acid and base. That's why saponification is such a good method, because it's pretty adaptable to what you have in order to make it. So as far as ester hydrolysis, let's start with acid, because that's what we did with ester esterification. So we're going to start with our ester. Go ahead, react it with acid. It's going to do generally the same thing as every carbonyl group ever does, ever. Oopsie daisy. Other way around. This negative is going to go here. You're going to go ahead and deprotonate it to fill this out. So ester hydrolysis again starts off with that Gem-Diol formation, as you can see, because now we have our OH, our OR group, and our methyl. Now we go ahead, react it with acid again. And the oxygen is going to go ahead and take that. So we have OH, OR, H, OH. This is going to become the leaving group. And essentially we're going to have OH. That's positive, and we're going to use our conjugate base in solution to go ahead and clean up, which is going to go Any questions on acid-catalyzed ester hydrolysis? No? Yeah. Yeah. No, I drew that wrong, right? So essentially this bond goes here first, and then from the oxygen it becomes negative. You take that and then you put it into the double bond. So I kind of skipped a step. So essentially those electrons are going down, but they use the oxygen as a stepping stone. So the acid takes the hydrogen and deprotonates it. The electrons from the bond between oxygen and hydrogen jump onto the oxygen's valence, making it negative. You use resonance to shift that back down to create the double bond, and that fills out the carbocation. Now, base is not too bad. Base, again, because you're starting out with a nucleophile, you can go ahead and just do a nucleophilic attack off the front end, and it actually simplifies the process quite a bit. So, right? And this comes in, and then that's going to go here, and that creates the leaving group. And now we have, and we can use OR negative to pick that up and send that there. Honestly, you're done here once you have the carboxylic acid. This extra step is called, it forms a carboxylate anion, which is important to know because this also helps you react with other things. And that's what the carboxylate ion is, what's used in saponification. And so that creates our and that's which is saponification. Okay. Any questions on that? We good? Huh? All right. All right. Moving on. Okay. So going on. So the last thing we have really is enolates and enols. Once we get that, we're good, guys. So ideally, when we're talking about enols and enolates, so we have our double bond OH. This is an enol, while our this is an enolate. Right? So essentially, they're just tautomers of the carbonyl group, and they differ in position in the pi bonds. So in a way, you could say they're the same thing, just different variants of each other, okay? So based off of that,
What would the in between these, say if you already moved the double bond down, but then you have the negative on the O?
move the double bond down and then have the negative on the O. I mean, in a way that is an enol, but you still protonate it.
Okay.
So you're not quite, because in a lot of the reagents you see, or the reactions, you don't stop at that step because you always treat it in water, so you can always protonate it, so it doesn't stop with the oxygen being negative. Yeah? Okay. So let's talk about tautomerization. How do we create enols based off if you're an acid or base? So if we're an acid, again, we start with our carbonyl, and we're going to react that with hydronium. Right? So when an acid, the hydrogen also gets pulled off of the acid straight onto the oxygen. And we're going to note on that, right? Just remember that there's always that hydrogen there. And so when we do that, this comes over. And so now we have our double bond OH positive. And we have our alpha proton. So essentially, we go ahead, resonate this. And that gives us our carbocation. And once we have the carbocation here, we're going to use this position here because that leaves us prime for reactions. And so we can go ahead and treat this with water, where water will go ahead and deprotonate that. And so that leaves us with the enol plus hydronium. So that's enol. Okay? Yeah, so pretty much I broke this bond and I moved that there. Yeah, deprotonated with water. So now we have the tautomerization in base, which is when we have our straight up hydroxide. So with the base, this one is simply just here. And from here we can go ahead, move that here, move that up, treat with water. Okay, so that's tautomerization, and now we have enolates, right? And so ideally with enolates, the general reaction with enolates is following that of tautomerization, right? Where we have the alpha, and we take a base, but we don't react it all the way. All we do is we take that, and just with tautomerization, we just stop right there, because now we have that, and this is the enolate. And so essentially, from here, once you create an enolate, all reactions just have an electrophile, and you do a nucleophilic attack. And that's another way of adding a substituent onto a carbonyl group, is through enolate formation. While if you did the same thing with an enol, instead of protonating, what you can do with the enol is, again, nucleophilic attack instead of that, and you're left with O bond. That. Those are the generals. Okay. Okay, so let me talk about some real quick facts real quick, and then we'll close and wrap it up. And I will also give you a short list of the topics I didn't manage to cover because we ran out of time, okay? So, kinetic enolates versus thermodynamic enolates. Right? So essentially, kinetics are always favored. Okay, so let's talk about kinetics. So kinetic is going to be favored by strong non-nucleophilic bases, such as LDA. Which is LDA. And so when you have the kinetic, your kinetic is always going to be the less substituted alpha hydrogen. Yeah, for kinetic. While thermodynamic, is going to be strong bases such as sodium ethyl oxide, right? Oh, yeah, sorry. Right? And this will do more substituted. And this is also the major product. It's more stable. Okay. Okay. You guys good with that? All right. So essentially, we're out of time, so I got to wrap it up. But we actually did really good. All that is left for us out of Orgo 2 that you missed, so what did we miss? We missed, because it's impossible to go through all of Orgo 2 in 2 hours. We have the Adol reaction, so I recommend looking this over, intramolecular and extramolecular. And then you have the Clenson reaction. And essentially after that, you have electrospec. We did not get through any electrospec, but electrospec is a priority. I would say you're going to get around, take it with a pinch of salt, around 5 electrospecs. So know your carbonyl derivative electrospec, know your conjugated system electrospec. All of this stuff is in your textbook, okay? I mean, Michael's is on there, but it's not covered to any grand extent. So I would say I'm going to write it on there. So Michael's, look over it, but it's not something you need to prioritize, because again, that's when you start aiming. Usually it's chapters 16 through 24 that are covered in grand depth. Yeah. I'm just... all right, guys. Thank you for coming, and good luck on your finals. If anybody wants to take any pictures of the notes or my base notes, which go a little more in depth, I'll let you do that, and we can go on and head out. Yeah, so yeah, they're all backwards, so